Hello and good evening. Welcome to this channel where we'll be looking at our physics. We're having a physics class right now. The topic of the class is going to be specific heat capacity. We will be looking at specific heat capacity. This is going to be our first lesson in our series. So we're looking at specific heat capacity, lesson 1. So we're going to take specific heat capacity from scratch. So please, if you've not subscribed to this channel, I would like you to subscribe and like the video, click on the bell icon so that you will always be notified whenever we upload a new video. So if you have any reason to connect with us, you can connect through the WhatsApp number or through my Instagram account, which is there. If you have any question at the end, you can drop them in the comment section. So please, you can invite others to join us in this class. Any physics, maybe you're preparing for a physics exam, JAMB, NECO, WAEC, IGCSE, might be foreign, might be local, or you are offering physics at one level or the other. This is a good class to attend because the topic is quite well broken down. So we're going to go right away and commence our class right now. Okay. So hello and good day to you out there, wherever you are in the world. This is Engineer Sam Manekan, also known as Ed Sam, welcome you to this lesson. This lesson is going to be on physics. So wherever you are, whether you are writing JAM, writing WAEC, writing NECO, or any other exam, IGCSE, or you are doing physics in school, this lesson will be of great benefit to you. So we'll be looking at a specific heat capacity. Okay, so this is our first lesson, so I'm going to introduce a lesson and we're going to breeze through it gradually. This is our lesson 1, so we're going to have subsequent lesson. So please, before you go on, make sure you subscribe to this channel, you like the video, you share it with your friends. Okay, so like I said, we'll be looking at specific heat capacity. Before we move on to specific heat capacity, what is heat? Heat is actually a form of energy. Just as we have mechanical energy, we have sound energy, we have light energy, we have chemical energy. Heat is a form of energy. Energy can do work, so heat can also do work as well. So heat energy can be transferred from one body to another. So let me take a scenario whereby we have two bodies, body A, which is made of copper, and body B, which is made of gold. Let's assume that body A is at a temperature of 25 degrees Celsius initially, and body B is also at a temperature of 25 degrees Celsius. This is the initial temperature, 25 degrees Celsius, 25 degrees Celsius. Okay, now if you bring body A and B in contact with one another, what is going to happen? Nothing will happen. It will not be transferred from body A to body B. Why? The reason being that both bodies are at the same temperature. There is no temperature difference. 25 minus 25 is 0. For heat to be transferred, there must be a temperature difference. But in this scenario here, 25 minus 25 is 0. So there is no temperature difference. So when both bodies are brought together, nothing is going to happen because they are at the same temperature. The driving force for heat transfer is temperature difference or temperature gradient. For heat to be transferred, there must be a temperature difference, there must be a temperature gradient. So take note, the driving force for heat transfer is what? Temperature difference. So here, heat is not transferred because there is no temperature difference. But let's assume now that along the line, the temperature of this gold rises to 40 degrees centigrade. What is going to happen when it rises to 40 degrees centigrade? And now these bodies are now brought in contact with one another. When they are brought in contact now, and this is case 2, 25. Copper is at 25, gold is at 40. So when they are brought in contact with one another, what is going to happen is that gold is at a higher temperature, copper is at a lower temperature. So gold will lose heat while copper is going to absorb the heat. This copper will absorb, gold will lose. So the temperature of gold is going to drop. That of copper will start increasing till this will drop 39, 38, 36, this will increase 26, 27, 28, till it will get to a temperature whereby this will increase to temperature, this will decrease to that same temperature. Like I'm just suggesting, it's not that it's going to be, but let's assume now, maybe when this rises to 31 to 30, let's say 32 degrees Celsius, and this will also decrease to that 32 degrees Celsius. There will be no decrease, there will be no increase anymore. So they will now be at equilibrium. So this will decrease to a particular value. This will also increase to that same value. Okay. So at the end of the day, there was a loss in heat here. This lost heat. This absorbed heat. So that is how it is actually transferred. For heat to be transferred between two bodies, both bodies must be at different temperature. It's just like now, let's assume that somebody is feeling hot, somebody who is ill. When you who is okay, who is alright, your own temperature is normal, but the other person's temperature is running a fever, is higher. When you embrace the person is going to transfer the heat in his body to you. You shout, your body is too hot, because some of the heat has been transferred to you. You've now actually felt that heat. Okay, so like I said, heat is measured in joules. Energy is measured in joules. So heat being a form of energy is also measured in joules. Joules. The symbol for joules is J. So you can have 50 joules of energy, 1 joule of energy, 2 joules of energy, 0.1 joules of energy. Energy is measured, like I said, in joules. Okay. So now, like I said, that there must be a temperature difference before it can be transferred. In the original case 1, body A, copper, and body B, gold, were at the same temperature. 25 minus 25 is 0 degrees Celsius. So in this case, there is no temperature difference. So that was why heat could not be transferred. In the second instance, gold was at 40 degrees Celsius, copper was at 25. 40 minus 25 gives you 15 degrees Celsius. So there was a temperature difference of 15 degrees Celsius. That was why it could be transferred from gold to copper. Okay. So like I said, take note, especially in your objective questions, they might ask you, what is the driving force for heat transfer? The driving force is temperature difference or temperature gradient. Okay, so heat can never be transferred when the temperature is constant or remains the same. Okay, so I've actually explained using somebody who is healthy and somebody who is feverish to explain heat transfer. So from here, we'll move into heat and thermal capacity. Heat and thermal capacity. Okay, so we'll be looking at heat and thermal, heat capacity and thermal capacity. Another word that can be used in place of heat is thermal. Thermal means heat. Heat and thermal are two words that can be used. So we'll be looking at heat and thermal capacity. Heat and thermal capacity, which is a subtopic under specific heat capacity. So we are going to continue right now. Used interchangeably. So heat capacity and thermal capacity are essentially the same thing. So heat and thermal capacity, like I said, are essentially the same thing. The heat or thermal capacity of a body is actually the quantity of heat Q required to raise the temperature of the body by 1 Kelvin. Like the heat or the thermal capacity of a body is a quantity of heat, the amount of heat that is required to raise the temperature of that body by 1 Kelvin. So let's assume now that I have a body A at 280 Kelvin. Body A is at 280 Kelvin. And I have a body B at 281 Kelvin. Okay? Sorry. I have a body A originally at 280 Kelvin. That is state 1. Then the temperature of body A now increased to 281 Kelvin as state 2. Now, the amount of, before this temperature can rise, that means heat has been added to this body. Now the increase is 281 minus 280, which is 1 Kelvin. The amount of heat that I added to this body A to raise the temperature of body A from 280 to 281, that is a temperature difference of 1 Kelvin. That amount of heat can be defined as the heat capacity of this body. Let's assume that I added 5 joules. So that means that the heat capacity of that, if I added 5 joules of heat and temperature increased by 1, then that means the heat capacity or the thermal capacity of body A is 5 joules per Kelvin. The heat capacity of body A is what? 5 joules per Kelvin, because for the temperature to increase from 280 to 281, I just added 5 joules of heat. So the heat capacity or the thermal capacity is 5 joules per Kelvin. So heat capacity is going to differ from bodies to bodies. It's going to depend on the body in question. So heat capacity, thermal capacity for different bodies are different. Heat capacity is measured in joules per Kelvin. Thermal capacity is, or heat capacity is actually measured in joules per Kelvin. Okay, so mathematically, let's write down an mathematical expression for heat capacity of a body. the mathematical expression for the heat capacity of the body. Heat capacity, symbol is C. Heat capacity is equals to the quantity of heat over the change in temperature, theta 2 minus theta 1. Theta 2 is the final temperature. While theta 1 is the initial temperature. So the quantity of heat supplied to that body divided by the final temperature minus the initial temperature gives you the heat capacity of that body. This is heat capacity is in joule per Kelvin. Quantity of heat is in joules. Then this temperature is in Kelvin. Okay, so that is the expression for the heat capacity of a body. So we are going to move on now to the specific heat capacity of a body. So we're going to move on to the specific heat capacity of a body. So we move on to specific heat capacity. What is specific heat capacity? The word specific implies that it is assigned to something is peculiar. So specific heat capacity of a body can be defined. When I write SHC, I'm just abbreviating S specific heat capacity. The specific heat capacity of a body or a substance can be defined as a quantity of heat that is required to raise the temperature of 1 kilogram of that body, of that substance, by 1 Kelvin or 1 degrees Celsius. The specific heat capacity of a body or a substance can be defined as a quantity of heat that is required to raise the temperature of 1 kilogram or a unit mass of that substance by 1 Kelvin. Okay? I hope that is taken. So 1 kilogram is the same thing as unit mass. When you hear the word unit has to do with 1. So 1 kilogram is a unit mass. So let's take it that let me explain this definition. You have 1 kilogram of, let's say, water. Now, how much heat will be required to raise 1 kilogram of water to change the temperature from, let's say, 271, an initial temperature of 271 Kelvin to a final temperature of 272 Kelvin. This is theta 1, this is theta 2, final, initial. How much heat do you need to raise water, 1 kilogram of water, from this temperature to this one? This is 271, this is 272. That is a temperature difference of 1. 272 minus 271 is 1. So theta 2 minus theta 1 theta 2 minus theta 1, this is 1. 272 minus 271 gives you 1 Kelvin. Even in Celsius, that is what it's still going to give you. When you convert this into Celsius, it will still give you 1 at the end of the day. So how much heat do you need to raise this 1 kilogram of water by 1 Kelvin? Let's even assume if water was at 20 degrees Kelvin. Let's say water was at 300 Kelvin. and temperature is raised from 300 Kelvin of that water, that 1 kilogram of water is raised from 300 Kelvin to 301 Kelvin, how much heat? The heat will be the same. As far as you are raising it by 1 Kelvin, the amount of heat you need to do that will be the same. As far as it's water, for water, the amount of heat that you need to raise the temperature of water from 271 to 272 will also be the amount you need to raise it from 300 Kelvin to 301 Kelvin. As far as it's a difference of 1, increase of 1, the amount of heat will be the same, will be constant, will remain the same in each instance as far as you are raising it by 1 Kelvin. So what's this amount of heat? And that body is 1 kilogram. So for water, you need 4,200 joules of heat to raise 1 kilogram of water by 1 Kelvin. So this is fixed for water anywhere, this is the amount of heat energy you need, this is the amount of heat energy that you are going to require to raise the temperature by 1 Kelvin. Okay, so you have for water, that is 4,000, the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. This is fixed. This is anywhere you go in the world, this is going to be the specific heat capacity of water. Okay, this is going to be what? The specific capacity of water. Okay, so like I said, copper has its own specific capacity. I think that of copper is around 380. The specific heat capacity of copper is around 380 joules per kilogram per Kelvin. That is the specific heat capacity of copper. Okay, so this is the specific capacity of copper. Anywhere in the world, if you go to Spain, you go to China, the value for copper will remain the same. So if they tell you that the specific heat capacity of copper is 380 joules per kilogram per Kelvin, what does this statement mean? This statement means that for you to raise the temperature of 1 kilogram of copper through 1 Kelvin or 1 degree Celsius, that you need 380 joules of heat. Finish, nothing more than that. So I believe this is understood. Okay, so like I said, water has a heat capacity of 4,200 joules per kilogram per Kelvin. If it's in grams, that will be 4.2 joules per gram per Kelvin. Okay, so I believe you're actually understanding what we're doing. So now, how do we measure its specific heat capacity of a substance? How is it measured? So in this lesson, I've actually explained the concept. I've explained concept of heat. I've explained heat capacity. I've explained specific heat capacity. So we're going to, in the next lesson, we are going to solve some calculations and look at how the specific capacity is actually measured. There's what they call the method of mixtures, which is used to do that based on conservation of energy, that energy is neither created nor destroyed. That is the principle of conservation on which this method, the determination of the specific capacity of a substance, is actually based. So I hope, watch out for the next lesson, which is coming up very soon. So you will join us as we look at some calculation and how to calculate the specific capacity of a substance. Thank you so much, and please subscribe if you have not yet subscribed. And if you have any question, you can contact me on the WhatsApp number there, or via my Instagram handle, or drop your question in the comment section and I'm going to respond. Okay, so in case you need the lecture materials for this thing, because I know it seems what I'm writing on the board is not so clear. You can let me know, and I'm going to send it forward it across to you. Thank you so much for joining us for this class. Bye. So in case you've not subscribed to our channel, please subscribe and like the video and click on the bell icon so that you always be notified whenever I upload a new video. Thank you so much for joining us this evening. God bless you and bye. So join us for lesson 2 of this class. Join us for lesson 2. Watch out for lesson 2 and join us.